So first we'll be seeing what perceptrons are, and then we'll go to different types of perceptrons. Like the first being just a single layer perceptron, where you have only the input layer and the output layer with no other additional layers in between. Then we'll be going into multi-layer perceptrons, which has at least one or two hidden layers between the input and the output layers. And then from there, we'll be going to CNNs. So CNNs basically are CNNs, that is convolutional neural networks, are basically very similar in their functioning to multi-layer to perceptrons. But the only difference is that they're usually used for images. So because of that, when you compare images with perceptrons, perceptrons
I think Sundari, your voice is lost for me. I don't know about other.
Yes, yes, we also can't
Okay,
hear.
okay, 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 okay.
I think she might lost connection.
Right, right. I'll just call her actually.
Okay, okay.
hello.
Yeah, yeah, Sundari. Actually, we lost you. Maybe you can start or from the start. You can continue from the start.
Okay, okay, cool. So
Yeah,
where
and
exactly did you lose
yeah,
me?
no, no. I think no, no. I think from the very just after you started, your voice was not audible.
Oh, okay, okay, okay.
Okay, we can start from the beginning, and then maybe you can put it in full slide, like so it will be more visible. That slide share, no? Yeah, yeah, that's better.
Yeah. Okay. So yeah. So basically, we'll be seeing three different kinds of networks in today's demo. We'll be seeing a single layer perceptron, which is a very simple perceptron, which has only an input layer and an output layer. And then we'll be moving on to multi-layer perceptron, which has an input layer and then some hidden layers, and then you have the output layer. Then we'll be talking about something called as convolutional neural networks. So maybe I'll start with the slideshow, and then when we start going through it, you'll be able to get a better idea about why we need so many different kinds of architectures. So before that, just a quick recap. So I'm guessing, sir, already did take all of those neuron models. So as you keep progressively simplifying them, you come up with something called as the model. So in the McCulloch-Pitts model, it basically treats the neuron as a black box to which the inputs are sent. So it receives input from all of the other neurons around it, and it basically just sums it up. Now, when this sum is greater than a set threshold, it reaches excited state. Otherwise, it remains in the resting state. So this results in a very binary model. So McCulloch and Pitts actually use this in order to model logic gates like AND gate, OR gate, etc. However, the problem is it can model very small, very simple functions like AND gate, OR gate, but it cannot model other data because there is no learning present. That is, it does not adapt itself to the data that comes in. It basically, you have a set of connections that are frozen for that input available. So there's no generalization. So if you used it for a similar data, but data that was unseen to the network, then the network will not be able to perform. So here is where they brought in this thing of learning. So basically what you have is you have the inputs that go into the neuron where they get summed up, and then you get the output. Now, if you just leave it at that, that is your McCulloch-Pitts neuron. But if you take that output and you compare it with the desired output for the input, and then change, and then the error that comes out of it is used to change the connections between the inputs and the neuron, then that results in a perceptron. So first we'll be seeing a simple perceptron which has no hidden layer. it has just an input layer and an output layer. And there's simple weight connections joining the input to the output, and they get summed up, and the sigmoid activation function is done over them, and then you get the output. So this because it's a very simple structure, it can be used with very simple data, like linearly separable data. So let's see a demo of that. Okay, so first let's take some data. I'll first show you the data that I'm using for this. Yeah, so can you guys see the figure?
Yes, yes, yes.
Okay, so this is the data that we have. So here you can see you have a cluster of points. Some of them are red in color and some of them are black in color. So the black color data is belongs to class B, and the red color data belongs to class A. So now the problem that's given to your network is to classify both. Now you will present each of these inputs separately to the network, and then change the weights in the network such that it starts approximating this and gives the actual output. Now the output here will either be 0 or 1. 0 for class A and 1 for class B. Now, once we train it in this way, some test data that is unseen by the network will be presented, and the network's performance on that data will be seen. So let's see how it happens. So now we saw that we got the data. Now we set the different parameters of the network. We use 70 epochs for training, and that is the number of input presentations to the network is 70, and you initialize the W at some random value, and then you present it to the network, present the data to the network, and you run it for 70 epochs. Now let's see what happens when we do that. So this blue line here is the output from the network. It's the decision boundary that the network is approximating. So you can see as the epoch number keeps increasing, the decision boundary gets better and better. This is where it was initially in your first epoch, and this is where it has finally come to. And this is the learning curve. So this is plotted as error versus the number of epochs. So as you can see, during the initial set of epochs, the error is pretty high. And then after that, it drastically starts decreasing, and then it kind of saturates after a while. So for this network with these weight initializations, it's saying that with just 20 or 30 epochs, it's able to learn the data very well. Now let's see what happens if you pick some other initialization. Now this is the initial way that the weights were, and this is the initial decision condition. Now let's see how it's moved on. Okay. So now you can see that the performance of the network was pretty bad. So the decision boundary was supposed to be here, but it's completely in a different way. So this illustrates the importance of how you initialize your weights. So for some weight initializations, very less number of epochs is enough for it to learn the problem. But for other weight initializations, might be completely different from what your data needs to be. So because of that, your learning might not be proper. So you have to take care that you initialize the weights properly. So now this was for linearly separable data. So what I mean by linearly separable data is you can, with just a linear decision boundary is enough to classify the data. So just a simple line is enough to classify this data. That's what I mean by a linearly separable data. Now let's use the same network, but with a different kind of input. Does anybody have any doubts until now? Okay, I'm guessing no doubts, so I'm going to go ahead with the next one. Okay. So first, I'll just visualize the nonlinear data that I want to give to the network. Now, this is the data that I want to give to the network. Now, as you can see, this is kind of a nonlinear data, so you cannot just use a single simple line in order to classify it. So let's see how the network is able to perform with this data. So I'm not changing any of the parameters here. I'm using the same learning rate. I'm using the same number of epochs, and I'm using the same number of outputs, number of inputs, and same number of weight connections and everything. So let's see what happens now. So this is your data, and this is your network performance across 70 epochs. So as you can see, it's not decreasing very much even after 70 epochs. As you can see, the difference is like in the order of 10 power minus 4, more than 10 power minus 4. That's where it's actually decreasing. So with this kind of a simple network, it's not able to classify the data. So this is what I meant by your perceptron cannot be used with non-linearly separable data. It can only be used with linearly separable data. So in order to rectify this, what they did was they came up with a multi-layer perceptron. So this, I'm guessing you guys have heard of the universal approximation theorem. So that basically states that however nonlinear your data is, if you have enough number of hidden layers, your network should be able to understand the data and classify it perfectly, fit the data perfectly. So in this multi-layer perceptron, you have hidden layers between the input and the output layer. And depending on the complexity of your data, the number of hidden layers and the number of nodes in each hidden layer can be varied. But there is kind of a trade-off in how much hidden layers and how many number of nodes in each hidden layer you can have. We'll get to that in a second. Let's see what happens if we use the same data with a multi-layer perceptron. So in this multi-layer perceptron, I am taking three hidden layers. So it has one input layer with two nodes, one output layer with 4 nodes in it, and then three hidden layers with 16, 8, and 4 nodes in each of it. So 1 second. Okay. Now let's see how this is able to perform with the given data. So this is the figure 1 represents the data itself, and the next figure here, the control figure, shows you the training loss as you keep increasing the number of epochs. Now another parameter that this will take a little bit of time for it to plot, but so as you can see here, this is the training loss and this is the validation loss at epoch 1. So what validation loss basically is so if you, let's say you have 10,000 samples in your test set. So common practice is to split the training data set into two data sets, training and validation set. So the reason why you want to do this is you want to learn the training data that's available to you, but you don't want to memorize it. If you memorize it, then you will not be able to perform well in your testing set. So that's the reason why they split the training data into training and validation set. So as you can see, so the network is basically trained on the training set, and those learned parameters for each epoch is tested on the validation set. Now this navy blue line shows you the training set loss across epochs, and this light blue line shows you the validation set loss across the number of epochs. Now the number of epochs is set here such that it's left to the network to decide, and it will stop training once your network, the loss in the network goes below 10 power minus 2. Now this is reached at epoch 9 less than 10 power minus 2 amount of loss. So after this, the network will stop training, and these are the decision boundaries you've got. Now Now, as you can see, it's classifying it pretty well, except at the boundaries where you can see some of them are misclassified, like this point here and this point here. Otherwise, it's perfectly done. Now, if you guys remember, I told you that there is a trade-off between the number of hidden layers and the number of nodes each hidden layer can have. What I mean is, so I spoke a little bit about how you shouldn't memorize the data too much. So another problem that you can run into, so this memorizing of the training data is called as overfitting, where you have very low training error but very high validation error. That is, it's fitting your training data very well, that it's not able to work well in any other data. The other kind of problem that you can run into is called as underfitting. In underfitting, it's not able to learn the training data well because the number of hidden layers or the number of nodes in each hidden layer is not enough for it to learn the complexity in the data. So basically, overfitting is usually due to too many parameters and too many hidden layers or nodes in the network such that it's fitting the data really well. Well, and underfitting is that there's not enough hidden layers or not enough nodes in each hidden layer. So you have to make sure that you hit the right balance between the two. So this is also another reason why it's very important for you to understand how the validation loss is, because in overfitting you have low training error but high validation error. But in underfitting you have high training error and high validation error. Now it's important to understand this because the way to cure these two problems are pretty different. In overfitting, you can solve the problem by getting more training data. But in underfitting, having more training data is not going to help your problem because the problem is in the network and not in the data itself. So in that, increasing your parameters is more important. So it's pretty essential for you to understand what's happening in the network before you can start modifying the network in order to get you the right parameters. Now, I'll just quickly demonstrate how you can see if it's underfitting or overfitting. Now, the perfect parameters here that we've chosen is 2, 16, 8, 4, and 4. Values of R are 4 and 4. Now I'm going to increase this two hidden layers to 32 and 32. Let's see what happens now. The network will start overfitting. Okay, while it's training, if anybody has any doubts until now, you can go ahead and ask. Or you can leave it in the chat box also. As you increase the number of parameters, your complexity of the network is also going to increase. So the amount of computational power it's going to take is a lot. It's going to be a lot more. That's why you can notice that it's taking a lot longer for it to finish training and finish updating than it did before.
Yeah, right.
Okay, I'm gonna reduce it a little bit maybe because it's taking way too long.
Mm.
Okay, so while we're stuck here, so the assignment 2 deadline was
Yeah.
extended till today. So Sandeep, can we maybe clarify that why we said we?
I think probably we can do it in the after your presentation, no?
Oh,
So
okay.
it will be okay. What
What happened?
no, no, actually that will be coming in the recorded video. So that is why.
Oh, okay, okay. So yeah, now when you compare it with the, if you remember the previous plot, you can see that the training loss is pretty high, but it's almost close to the validation loss. But for the number of epochs, it's decreasing a lot faster. Last one, it took about 9 epochs for it to reach 10⁻². I think, I'm guessing this will take a lot quicker. But your performance in your testing set is going to be much worse than it would have been before. So,
Okay, one you are showing it for that reduced hidden layers, and then one is for the increased hidden layers, no, Sundari?
yeah, so this is for increased hidden layers. The next case will be for reduced hidden layers.
Right.
And when you, if you reduce the hidden layers, obviously the number of epochs that it takes to reach will also be a lot higher because your network is too simple for it to understand the complexity in the data.
Yeah, yeah, that's right.
Yeah, so as you can see here, there's not much of a difference between the validation loss and the training loss. So I'll quickly stop it right here and go for reduction in the hidden layers. So I have only 2 and 2 in both the hidden layers now. 2 nodes in both the hidden layers now. So as you can see, both training and validation loss are pretty high. Okay. And it's taking a lot longer for it to start converging. Even with 14 epochs, it hasn't reached the set accuracy. So again, I'm just going to stop it here. Yeah. So this is why it's essential for you to understand whether it's overfitting or underfitting, and also to split your data into validation and the training loss, training data set. So the next is also, until now we only saw two-dimensional data, but now we're gonna move into, okay, even the images are two-dimensional, but now we're going to move into something called as the MNIST data set, which basically contains handwritten digits. So this is how your data set will look like. They're grayscale images of different handwritten digits, like, and there's usually 10 classes ranging from 0 to 9. So you can use this with a perceptron also, or you can use it with a CNN. So let's see what happens when you use it with an MNIST. Okay, actually, I think I'm gonna skip that, and then I'm gonna go straight ahead to CNNs. So now, okay. Okay, so this is basically the architecture of a, this is like a common architecture that is there for a CNN. So you basically have the input and you have different convolutional layers, and then at the end you have few fully connected layers. So those fully connected layers are very similar to your MLP, but these convolution layers are a little bit different from your fully connected layers. So the fully connected layers contain, they're one-dimensional in nature and they contain nodes. But your convolutional layers are almost always two-dimensional in nature. And what happens when you use a convolutional layer with your image input is, instead of having the entire layer connected to each and every node in the input, it's connected through something called as a weight kernel. So you have a weight kernel that is smaller in size than your input and your convolutional layer, and that weight kernel is basically smeared all over your input. So the reason why we're doing this is an image can usually be broken down into separate features. Like for example, if you see this data set of, let's say you take comparing number this data with this data. Now 4 and 1, they both have this vertical line in common between them. But in 1, this vertical line is right in the middle of the image, while in 4, it's slightly shifted towards the right. But the features are pretty much are common. This feature of having a vertical line is common between the two images. So your weight kernel basically tries to locate these kind of features that are common in your images and in your data set, and tries to identify that. And your weight kernel, so if you train your convolutional layer in this data set, what you'll see is your weight kernels will start resembling at the end of training the different features that the images are made up of. So I'll quickly start running the program. So yeah, okay. So here, okay. So here I'm defining the parameters for a convolutional network. So image dimension is 28. That is the MNIST data set contains images of 28 cross 28 dimensions. Since it's grayscale, it has only one. There's no third dimension in it. And the number of classes is 10, that is ranging from 0 to 9 digits. And I'm going to be using just one convolutional layer with 20 filters in between. And the filter dimension is 9 cross 9. So when I say filter, I mean the kernel. So the kernel dimension is 9 cross 9, and there are 20 such kernels available. So then I'm going to load the data set. So once we load the data set, we can start training there and initialize the parameters that are there in the network. So now if this is your WC actually represents your convolutional network weights. WD is the weights between your convolutional stage and your fully connected stage. BC is the bias of your convolutional stage, and BD is your bias of your fully connected stage. So as you can see, there's not much of a difference between MLPs and CMNs, except for the fact that you have convolutional stages at the beginning, and then you have the fully connected layers. So once we've initialized that, we can start training. So as the network is training, we can start looking at what is actually happening inside the network. So yeah, so when you compare these images, there's other features that are similar in most of these images, like the vertical line that I was talking about. That's common in 1, 4, and 9, and this kind of a squiggle at the top is common between 3 and 2, and the squiggle at the bottom is common between 3 and 5. So your weight kernels start shaping up to understand that these are the features that are important in your data set, and starts mimicking them. Now this is similar to what kind of happens in your brain with respect to the visual cortex, as you have cells there which respond to particular orientations of bars that are found, that can be found in the visual space that around you. So that's basically what this weight kernel will do at the end. Now, how the weight kernel actually is used is, it's going to be smaller in dimension when you compare it with your input or your output. Now, it's just taken from one space, one place of the, it's placed on one place of the input, and element wise multiplication occurs between the values in the kernels and the values at the input, and the sum of all of those elements comes out as your output. Like if you can see here, this is the filter or the kernel that you're using, and I'm first placing it on this 3 cross 3 position in the image. And then I multiply them element wise, and the sum that I get here, 0, becomes your first output here at the first convolutional stage's first output. So those are called as the feature maps. So this process is basically repeated by using the filter and moving it over the entire image. And you can choose whether you want to start from the first and then next skip to this, or start from here and in the next stage go to here. So that's called as the stride length, and using different stride lengths will result in different sizes of this feature map. And the performance of your network will also change with respect to that. So in case you have an RGB input, then the filter that you use, so in RGB input, your image will have a width, height, and also a depth. So for each of the R, G, and B channels. So based on that, because of that, your weight kernel will also be three-dimensional in nature, but otherwise the logic remains the same. It's still convolved over the entire thing, but each of the three weight kernels correspond to each of the three dimensions in the image. Now, once you've convolved each of the filters with the input image, what happens is you get out the feature map, and this feature map is then sent to something called as a ReLU activation layer. So in this, if all the negative values are suppressed and only the positive values are taken, and then after that it's sent to a max pooling layer. So the reason why you want to go for a max pooling layer is because sometimes the features in an image might be repetitive. So let's say you have a cat in an image in the foreground while the background is completely grass or sky maybe. So in that case you have a lot of blue stuff or features that are relevant to the sky, but that's not actually important for your, that might not actually be important for your problem. So your max pooling layer takes only the maximum features, features with maximum weight, and suppresses the other ones. There's also other type of pooling layers. One is called as the mean pooling layer, where the mean of some of the submatrices of these will be taken and will be sent to this. So this is basically what happens in the fully connected layer. The features that you then get out of the convolutional stages are then sent again to the different layers in the hidden layer. Once you do all of that, you're done, then send it to the last output layer. So the last output layer, the number of nodes here will depend on the number of classes in your data. Now here in this particular diagram, there's only two classes, dog and cat. So in that case, after you get all of the weights and you sum all of it, you get a value, and that's basically like the probability value of the object present in the image. So if there's a higher probability for class 1, then that is classified, then that data is classified as belonging to class 1, and the error that you get is then used to change the weights.